Hello guys, in this video we were talking about Faraday laws. So before we talking about Faraday law, we should know who is Faraday. Faraday was an English scientist who discovered the electromagnetic induction in 1831. Faraday's law is the basic laws of electromagnetism. It's predicting how a magnetic field will interact with an electrocircuit to produce an electromotive force. This phenomenon is known as electromagnetic induction. So, what's the law used for? Actually, it can be able to calculate the electromotive force inducted in a circuit. So, let's explain it in more detail.
Hi guys, I'm Fareez. Today I will explain to you about the working principle and the application of Faraday law in daily life. For working principle, any change in the magnetic environment of a coil of a wire will cause a voltage or electromagnetic field to be induced in a coil. No matter how the change is produced, the voltage will be generated. The change could be produced by changing the magnetic field strength, moving a magnetic toward or away from the coil, moving coil into or out of the magnetic field, and also rotating the coil relative to the magnet. Faraday law also states that current will be induced in a conductor which is exposed to be changing a magnetic flux. So next, what is the application of Faraday law? Basically, Faraday law has a wide range of application, but for today I will tell you only 3 crucial applications of Faraday law in daily life. The first one is transformer, the second one is induction cooking, and the last one is electric generator. That's all, thank you.
Hi, let's continue our presentation of Faraday's law, which is the fundamental for all further chapters. Basically, Faraday's law is based on experiment, and the first Faraday's law states that when the magnetic field is linked with the conductor, changes of EMF are produced across the coil. So, here we can see the magnetic flux linked to the coil, and if there is a change due to its motion, then EMF is induced. But when there is an EMF induced between the 2 points, which is we can see over here, and we close this circuit by fitting a galvanometer, EMF will function to produce current, and if there is a path given to it, the current will flow through it. So the EMF generated here will have 2 terminals. One terminal will become positive and the other one will become negative. First Faraday's laws, there is 3 cases. So the first case is when the magnet is stationary, the galvanometer shows 0 reading. The second case is when the magnet moves towards the coil, galvanometer will deflect towards the right side. Here we can see the current flows in a positive direction. For the third case, when the magnet away from the coil, galvanometer will deflect towards left and the current is flowing in the opposite direction. 3 factors that cause to increase EMF in the coil. For the first one, increase the relative motion between magnet. The second one is by increasing the strength of a magnet. And the third one is by increasing the number of turns in coil. Moving forward to the next section, which is Faraday's second law. Faraday's second law states that the EMF induced across the coil is equal to the rate change of flux in the coil. And here we can see the formula, which is E, which is electromotive force, is equal to derivative of phi over dt. which is the phi is equal to magnetic flux and the t is the time taken. But if we notice, the direction of the EMS is opposite to the change of flux, so we have to put negative in the equation. This is a Faraday's law derivation. We have to consider a magnet approaching towards a coil. And the second one, we have to consider two time instances, T1 and T2. So, the first one, flux linkage with a coil at the time 1. T1 is equal to number of turns times magnetic flux 1. The second one, flux linkage with the coil at the T2. T2 is equal to number of turns times magnetic flux 2. The change in the flux linkage is given by n times the changes of magnetic flux, which is phi 2 minus phi 1. By considering this change in flux linkage as phi, so phi is equal to phi 2 minus phi 1. Hence, the change in flux linkage is given by n phi, which is number of turn times phi. So, the rate of change of flux linkage is electromotive force is equal to number of turn times phi over t. So, taking to derivative of the equation above, we get electromotive force is equal to n times derivative of phi over t. This is actually according to the Faraday's second law, which is Faraday's second law say that electromotive force EMF is equal to number of turn times the rate change of flux. That's all. Thank you.
Hi everyone, I am Adzreen and I will be presenting about the problem solving question. So the question you are seeing right now is what I am going to solve. So the information that we can extract from this question is that the radius is 10 cm and the number of turns n is 15 turns with the angle of 30 degrees and the magnetic field strength B at B1 is 1T and B2 is 5T with a time interval of 10 seconds. So the question asks me to find the EMF generated around the loop, and the second question asks me to find the current flow around the loop as the magnetic field is increased. So how we are going to answer this question is, first step is to find the area of the loop. So the formula is A equals to pi r square, and so we insert the value that we get from the question, which is 0.1, and then we insert and we get the pi multiplied by 0.1 square, then we get 0.0314 meter square. So secondly, we find the component of the magnetic field that is perpendicular to the loop, which is B equals to B cos theta. Then we set the angle that we get from the question, that which is 30. Then we get B cos 30 degrees. Then we get 0.8860. And thirdly, we find the initial magnetic flux that link the loop, which is the initial magnetic flux equals to NA B1 cos theta. And we set all the information that we get earlier, which is N is 15, the area is 0.0314, and the B1 is 1, and the cos theta is 0.8660. Then we get 0.4008 Weber. So the final initial flux, which is we only change the B2 value to 5. So we got 15 multiplied by 0.0314 multiplied by 5 multiplied by 0.8660. Then we get 2.039 Weber. So how to calculate the time rate of change of the flux is only that we deduct from the final magnetic flux with the initial magnetic flux. So we got the formula is d magnetic flux over dt. Then we get 2.039 minus by 0.408 divided by 10. Then we get 0.163 Weber per seconds. So how to answer the first question is to find the EMF generated around the loop is to use the formula which is the EMF equals to d magnetic flux over dt, which is 0. Then we get the answer of 0.163 volt. So lastly, to answer the second question, which is ask us to find the current flow around the loop as the magnetic field increase, we must use the formula of what I equals to EMF over resistance. So then we insert all the value that we get from the earlier question, which is the EMF is 0.163 over the resistance is 15. So we got the answer of 0.011 ampere. So that's all from me. Thank you.
My name is Ahmad from Zulmajdi, and I will be here to explain about the second question, which is a simple question about the Faraday's law. So truly from this question, the second question, it is just a simple question where it provides us with some information, which is the number of turns is given, which is 40, plus with the magnetic field with the value of 2 Weber per meter squared, and also the area is provided, which is 200 centimeter squared. So in order to apply into our Faraday's law equations of flux, we need to convert the centimeter square into meter square unit, which will become 200 times 10 power of negative 4 meter squared. So this simple questions is just can be calculated truly, where firstly we need to find the magnetic flux for initial magnetic flux with the formula of BA cos theta, which the B is 2 times with 200 times 10 power of negative 4 times with cos 60. The reason why we use 60 is because from the question it says that it rotates from original directions, whereas the 90 we need to minus with 30 degree. So we will have the degree of 60 degree. So for the initial flux, we will have the value of 2 times 10 power of negative 2 Weber. So next one, we will find the final flux, which is using the same equation BA cos theta, but the theta we need to change to 0, which is the origin one. So just BA 2 times 200 times 10 power of negative 4 times with cos 0 degree. So we will have the answer around 4 times 10 power of negative 2 Weber. So in order to find the EMF, like the previous question, we just find the rate of change of the magnetic flux per time interval. So we just minus the final one with the initial one. So for 4 times 10 power of negative 2 minus with 2 times 10 power of negative 2, and then we must time with the number of turns, which is 40 per over the time interval. So the final answer will be 4 volt. Okay, I think that's all for me. Thank you. Okay, so for the conclusion, we can understand that Faraday studies the induced electromotive force generated by the current change and relates the induced electromotive force to the rate of change of current. If the discovery of the law of electromagnetic induction is a major breakthrough in the history of physics, the distinction between motional and induced electromotive force has enabled people to understand a vortex electric field that is completely different from the electrostatic field, thereby enabling people to have a deeper understanding of inductions, the essence of electromotive force, and the research of self-induced electromotive force and the mutual induction electromotive force can further promote the application of electromagnetic induction. Okay, I think that's all from me. Thank you.